Hello and welcome back to the Science of Concrete Materials class. This is lecture number 28 of the class, and here we will continue our discussion on the fresh concrete properties. In the last lecture, lecture number 27, we started the discussion on the fresh properties, and we discussed, workability at length, the definition of workability, its implications on hardened concrete. We also discussed the segregation and bleeding. Also, we discussed the factors that influence workability and how to measure workability. In this lecture, we will finish one remaining topic about workability, which is the loss of workability, and then we will discuss the remaining fresh properties. Okay, so about the loss of workability. During the period of fluidity, there will be a steady decrease in workability with time, caused, partially by the hydration of C3S and C3A, which basically continues slowly even during the dormant period, if you refer back to the heat of hydration curve, and also partially by the loss of water from concrete through evaporation and absorption. Also, due to particle interactions, which basically change because of the presence of hydration products on their surfaces. This slump loss is approximately linear with time, although it is greatest in the first 30 minutes to about 1 hour after mixing. So since the slump at the time of placement is really of greatest importance, the slump loss of concrete must be considered when selecting mix proportions. So slump loss is increased when concrete temperatures are high and also when accelerating admixtures are used. In both cases, the setting times are decreased. Okay, so the accelerated slump loss can occur when water reducing and set retardant admixtures are used, even when the setting times are unchanged or even increased. You keep that in mind. So that the rate of loss of workability is less for lean mixes. Lean mixes, those are with low cement content, and when high water cement ratios are used. So the loss of workability is less in those two cases. Also, you have to keep in mind, as we have probably discussed before, the brand of cement is also important, since basically two cements of the same type can have different compound composition. So I am going back to emphasize something I have said about, when talking about workability and other fresh properties. Consistency and uniformity are important. Also, if the concrete mix is improperly designed, it may be necessary to remix the concrete with additional water, what's referred to as retempering, just prior to placement in order to restore workability. This is here a general statement, and I'm mentioning it just for the sake of completeness of the presentation. I do not by any means condone or encourage this practice, which is adding water to the mix at the job site. This should be avoided by all costs, should be avoided. If there is a potential for loss of workability for whatever reason, due to hot weather, the windy conditions, and whatever conditions are, that should be addressed during the design of the mix by basically selecting the proportions correctly, by using super plasticizers, by other means. but adding water at the job site should be avoided completely. End of the story, okay? Okay, so let's move on now to the setting of concrete. Let's define setting. You know, we have, of course, talked about the setting of the cement paste, if you remember, during the hydration lectures. Setting is defined as basically the onset of rigidity in fresh concrete. It is distinct, you know, from hardening, which describes the development of useful and measurable strength. So you have to keep, you know, make sure you're aware of this distinction. Setting precedes hardening, but it should be emphasized that both are gradual changes that are controlled by the continuing hydration of the cement. So this is just the explanation. Basically, we can view setting as a transitional period between states of true fluidity and true rigidity. Okay? So the figure I'm going to show on the next slide, you know, shows that, you know, initial set and final set, you know, which are basically measured according to ASTM C403. This is for concrete. Okay, this is, you know, this is the similar to the curve we have shown prior in previous lectures about the setting of the cement paste. Okay, so basically here is this initial set and this is the final set. This is, you know, the transition, basically the setting from the fluid stage to the rigid stage. Okay. The penetration tests, you know, used to measure the times of setting, which we discussed previously, are purely, you know, arbitrary measurements, and, you know, do not really correspond exactly to any specific change in concrete properties. Although it is useful to consider, you know, that initial setting represents approximately the time at which fresh concrete can no longer be properly handled and placed. Okay, while the final set approximates the time at which hardening begins, as I just mentioned. So remember that, you know, fresh concrete will have lost measurable slump prior to initial setting, while, you know, measurable strength will be achieved sometime after final set. That's how you think of these. You know, we think these arbitrary points, but that's how you think of these two markedly distinct, you know, points we just talked about. So what really affects the setting? It is obvious the hydration of the cement phases will affect setting. Definitely the C3S. So this, it should be remembered, you know, that cement hydration begins as soon as water is added to the mix. Okay? So setting is controlled primarily by the hydration of C3S. And, you know, the period of fluidity corresponds to that induction period, which is stage 2 we discussed previously, if you refer back to the heat of hydration curve. Okay, so setting occurs when the induction period is basically terminated and the rapid hydration of C3S starts, you know, in stage 3 again. Initial sets corresponds, you know, approximately to the beginning of stage 3 and the final set to its midpoint. I did not include a graph of that curve, but you could refer to it in one of the previous lectures. So initial set is marked by the beginning of the rapid temperature rise of the concrete, which reach a maximum rate at final set. All right. So setting is also accompanied by a decrease in electrical conductivity and an increase in the velocity of sound waves propagating through the paste. So the measurement of either of these properties, could form the basis for an adequate test for setting. Will those two terms about, the electrical conductivity and the sound wave propagation, we will talk about these tests in later lectures and what we use them for. But the behavior of concrete, measured with these two tests, actually can also shed some light about the setting times of concrete. Okay. Also, we talked about the role of C3S. Also, the C3A and the gypsum. Okay, they influence the time of setting. If you refer back to the hydration of the cement, lectures, you will refresh your memory on some of these subjects. So when using ordinary Portland cements, the 5 ASTM types, ASTM C150, C3A plays, relatively minor role in determining setting behavior, except, in the cases of abnormal set, like the flash set, which I'm gonna mention again here shortly. That gypsum is always interground with modern cements, so it reacts with C3A to help control the setting time. So when large amounts of yttringite are formed rapidly, the aluminate phase will decrease the time to the initial and final set. That's, when we're talking about when the amount of gypsum basically is not regulated correctly, or in the case, of expansive cement. So in extreme cases, yttringite formation entirely controls setting time. But I mean, in normal, in modern cement, conforming to ASTM, we do not really encounter this problem because the hydration of C3A is regulated by, the amount of gypsum we add. So we never encounter almost this flash set phenomenon. So the generally the abnormal setting behavior of concrete is rare nowadays. It was really a troublesome problem in the past, but nowadays it's really almost rare. So basically there are these abnormal setting behavior are most likely to be encountered under certain conditions when admixture is used, usually set retardant admixture. But right now, nowadays, you might encounter two major setting problems, which are the false set or the flash set. We talked about this. I will mention here just as briefly as I can about these problems. False set, if you remember, concrete may stiffen rapidly, a short time after mixing is complete. So in this case, fluidity is restored by remixing, and the concrete will then set normally after that. We will not have a problem. So false set is more of a nuisance than anything else. This phenomenon is basically sometimes referred to as plaster set because it is most often caused by crystallization of gypsum. When gypsum is interground with clinker, you remember when we make Portland cement, we get clinker, we interground gypsum with it, becomes Portland cement. Sometimes when the gypsum is interground with the clinker, the material in the grinding mill can get quite hot because of the high energy input during grinding. So the temperature can rise basically as high as 120 degrees Celsius, okay? Which will cause gypsum to partially dehydrate to calcium sulfate hemihydrate. You remember we talked about this. Gypsum is the dihydrate, and the other form of it is the hemihydrate or the plaster. Okay, so if this happens and gypsum is basically converted to the hemihydrate, when water is added, the hemihydrate will rehydrate back to gypsum and will form a rigid crystalline matrix. But however, there are only small amount of plaster in the concrete. Very little strength can actually develop, and the plaster can be easily disrupted by further mixing. Okay, so this is not really a major problem, but it depends. And again, chemical analysis like XRD analysis of the cement, if you are concerned, can confirm the presence of hemihydrate in your cement or not. Okay. The other phenomena, which is basically the flash set, we talked about it. If the C3A in the cement is very reactive, flash set or quick set may occur. Flash set is caused by the formation of large quantities of monosulfoaluminate or other calcium aluminate hydrate phases. So this is a rapid set that cannot be disrupted by further mixing, that indicating some strength has already developed. So flash set is more severe condition than false set. But fortunately, flash set has been largely eliminated as a problem, with the normal Portland cement by the use of gypsum to control the C3A hydration. But occasionally, the use of an admixture may increase the hydration of C3A to the point at which flash set may occur. Like when the C3A and gypsum contents are high, the formation of large quantities of yttringite can also cause flash set. So basically, that's something again that you need to be aware of about the chemistry of the cement you are using, and whether the C3A to the SO3 ratio has been correctly proportioned in order to prevent such behavior. And again, I said these problems are rare really to happen nowadays. Nonetheless, they could happen, and also it is good to know that the background for such phenomenon, so at least you might be able to explain what could happen in any situation. Okay. All right, so we finished the setting time. Let's actually move on to the remaining of the tests we do on the fresh concrete. Okay, we just have to keep in mind that tests on fresh concrete are carried out largely as quality control measure, and to help ensure that proper mixing or mixed proportions are being maintained. So the underlying assumption is that the tests on fresh concrete are useful for two reasons. First, they permit some estimation of the subsequent behavior of the hardened concrete, and also changes in the properties of fresh concrete imply that the concrete mix is changing, so that remedial action can be taken if necessary. We're talking about maintaining uniformity throughout the job. By far, the most common tests on fresh concrete are slump tests, or of course other workability tests, as we described previously. Here we will consider other fresh property tests that are carried out. As you can see here, the setting time test, the air content with the 3 different methods that can be used to measure it, and the unit weight and the yield. Okay, so before we move on to describing these tests, let's talk about the sampling of fresh concrete. Of course, sampling, no doubt, will impact the results of the testing and the consistency of the testing. As we have to keep in mind, concrete is a manufactured material, made from cement, aggregate, water, and admixtures in some cases. All of these ingredients are subject to variation, both in quantity and quality. So the first consideration in testing fresh concrete is that concrete tested to be truly representative of the batch we are testing. So this is, of course, very much a matter of judgment and experience. So it is difficult to lay down hard and fast rules to define what is representative. Also, samples must be taken reasonably often. A common requirement is that at least one sample must be taken for every, say, 115 cubic meter of concrete placed. Okay, a typical specification for sampling fresh concrete is the one described in ASTM C172, which covers sampling from stationary and truck mixers and from equipment used to transport centrally mixed concrete. The specification requires that tests to be done on composite samples. That is, samples taken at several points during the discharge of the concrete and then combined together to be tested. The main problem in collecting these samples is ensuring that they are not contaminated by the forms, the subgrades, and no segregation that have occurred during sampling. So one has to be really very careful and exercise consistency and reasonable care in collecting these samples. It is also important to carry out the sampling as quickly as possible, maybe within 15 minutes. So as workability, as we said, in particular, quickly changes with time. A minimum size of 1 cubic foot is required, for strength tests, but smaller samples are permitted, for air content and slump tests. Also, it is important not only to maintain reasonable uniformity, as I said, between different batches of concrete, but also to ensure that the variability of concrete from different parts of the same batch, which is basically the within batch variation, is also low. Okay, so we're talking about uniformity. This largely becomes significant when using usually older or worn out equipment, or where there is inadequate equipment maintenance, where you might have variation within the batch itself. There are stringent requirements for the permissible variations of ready mixed concrete in ASTM C94. Samples are taken from 2 locations in the batch, representing the first and last portions of the batch. These samples are tested separately, and the uniformity requirements are usually stated in that standard, so you can actually refer to ASTM C94. Also, it is, of course, normal to expect some variability in concrete tests and quality, as probably we will discuss in a different part of the class. So it may be stated here as a general rule that the less variability there is in concrete properties, the better. The less variability in the testing and in the sampling also. Okay, so let's talk about measuring, the setting time, measuring of the setting time. As we mentioned earlier, although the time of setting of concrete is an arbitrary measurement, it is an important parameter for a number of reasons. Because first, it is used to help regulate the times of mixing and transit. Also to gauge the effectiveness of various set controlling admixtures, either retarding or accelerating admixtures. Also to help plan the scheduling of the finishing operations. And again, we said about testing of concrete. Now you know what is the setting time of the concrete you are using. So it goes a long way when you plan when you order your concrete, knowing how long it's going to take you, for example, to place the concrete, cast it, and to finish it. So all that is very important for engineers working in the field to understand these limitations, to make sure they at the end of the day deliver good quality concrete. As we have seen, in a different part of the class previously, there are two tests in use for the setting time of cement. But unfortunately, these tests, do not correlate well with the setting time of concrete. This is due to the reason, that the current test procedure outlined in ASTM C403. In this penetration test is limited to concretes with slumps greater than 0 and to cases when the tests of the mortar fraction of the concrete will provide the information required. So there is some limitation here. And as described in ASTM C403. So to describe this method briefly, the test consists of removing the mortar fraction of the concrete by passing it through 4.75 millimeter, the number 4 sieve, rodding the mortar into containers, and then measuring the force required to cause a needle to penetrate 25.4 millimeter, 1 inch, into the mortar. Removable needles with bearing areas ranging from 645 to 16 millimeter square are used. This is done at regular intervals, and basically a curve of penetration resistance versus time is plotted. Times of settings, times of the initial set and the final set, are defined as the times at which the penetration resistance are 3.5 MPa, 500 psi, and 27.6 MPa or 4000 psi respectively. The first one for the initial set and the second one for the final set. Although these are, as we said, arbitrary chosen points, the 3.5 MPa corresponds approximately to the point at which concrete will no longer become plastic under vibration. Okay, let's talk about the air content measurement. The air entraining agents have been already, as you remember, discussed in the second module of the class during this talk about chemical admixtures, and the effects of the air entrainment itself on durability will be discussed later in the durability module of the class. This section here of the class deals only with the techniques available to measure the amount of air in concrete. It must be remembered, though, that in air entrained concrete there will be two types of air: entrained air and entrapped air. The test methods described next here in this section of the class are unable to distinguish between entrained and entrapped air. They simply measure the total air content. Also, the air content, it is expressed in terms of the volume of concrete. Okay, although as we know, the air is present only in the cement paste, so that you have to keep these things in mind. Okay, it also should be remembered that we have, as you know, we already described a test for determining the air and training potential for cement, if you remember. Unfortunately, you know, an air entraining cement meeting those requirements of that test may still not give the required content, air content in concrete when tested by these methods. So there are three principal tests available to measure the total air content of concrete. First, the gravimetric method, the volumetric method, and the pressure method. All right. Let's talk at the first one, which is the gravimetric method, according, you know, to ASTM C138. Okay, this method, as I said, you know, for determining the air content as per ASTM C1C38. This is the oldest and simplest method. It consists basically of comparing the unit weight of concrete containing air with the calculated unit of air-free concrete, basically computed from the proportions and the specific gravities of the mixed components. All right. The air content of the concrete, referred to as A in this equation you are looking at here, basically calculated as you say, A, which is T minus W over T multiplied by 100, which is T is the theoretical weight of concrete on an air-free basis, and W is the weight of concrete, the unit weight of concrete. This method can also be used to basically determine the yield, meaning the volume of fresh concrete produced from a known quantity of ingredients, and the cement content as well as the unit weight. This test is not really suitable for field measurement, for field use, since basically it requires an actual knowledge of the specific gravities of the ingredients, and also the batch proportions and moisture content of the aggregates must be accurately known. So it may not be used, also with lightweight aggregates, since their specific gravities are very difficult to determine accurately. However, the test is suitable, for laboratory work where the other parameters may be measured, accurately. Okay, this is, this photos here show basically what goes on into the determining the test. The next test is or the method is the volumetric method. The volumetric method, per ASTM C173, is based on comparing the volume of fresh concrete containing air with the volume of the same concrete after the air has been expelled by agitating the concrete underwater. Basically an apparatus is similar to the one shown here in this figure is used. And again, for more details, you could refer to ASTM C173. So what happens, a sample of a fresh concrete is routed into the measuring bowl, which have a volume of about 0.07 cubic foot or 0.002 cubic meter. Okay, what is the measuring bowl right here? The excess concrete is struck off, the top section is clamped back in place, and water is added to the zero mark right here. All right. The unit is then inverted and agitated vigorously until all the air seems to have been removed from the concrete and has, risen to the top of the apparatus. 1 cup of isopropyl alcohol is then added to dispel, bubbles, and a direct reading of the air content can be made by reading, the amount of liquid remaining in the neck of the apparatus, which of course after, correcting for the amount of isopropyl alcohol added. The main difficulty of this test, though, is the large amount of physical effort required to remove the air from the concrete. Nonetheless, it is used and can be done. The other method is the pressure method, as per ASTM C231. This is the most common method for measuring the air content of fresh concrete in the field. The basis of the method is the measurement of the change in volume of concrete when subjected to a given pressure. So this change in volume is assumed to be caused entirely by compression of the air, and the principle of Boyle's law can then be used to calculate the air content. It's a simple test, though. Typically an apparatus similar to the one shown here in the figure is used. The concrete is consolidated into the measuring bowl and struck off level to the rim. All right. And the apparatus is then reassembled. As you can see, it looks complicated, but it's not. The water is added through the petcocks, okay, and the test pressure, applied and adjusted using the air bleeding valve you can see here in the figure. The pressure is released until the air content, stabilizes and the air content is read. This, gives a value called the apparent air content, referred to as A1 here. I'm referring to it. Similarly, the air content of the aggregate itself is A2 is determined basically for porous aggregate. I mean, the normal aggregate may not be really a problem, but in case of porous aggregate, we have to measure it. Then the true air content is simply, the difference between the two values. The main advantage of this method is that it is not necessary to determine the specific gravities, moisture content, or mixed proportions of all components. If the air content of the concrete exceeds the range of the apparatus, the determination can be repeated basically at a lower test pressure. Simple. It should be noted that these tests measure only, as we said, the total volume of the air in concrete. They yield no information about the nature of the air void system. Okay, but as we have seen in previous discussions, it is the nature of the air void system, meaning the pore size and the pore spacing, that really determine the durability of the concrete. If you remember back from the air entraining agent under the chemical admixture lectures, if you remember about the distribution of the air bubbles, the size and the spacing, that's really what determines the level of durability of the concrete. So in order to determine these, they cannot be determined by this method because it only measures the total content of the air, as we said. So to determine these, it is necessary to examine the void system of the hardened concrete itself. This can be done using the procedures described in ASTM C457. Okay. The next test is the unit weight of the concrete. and the yield. So as we remember, the density, which is the unit weight of the fresh concrete, can be determined by weighing a known volume of the concrete. So it is, as you remember, it is usual to weigh the sample of concrete used for the air measurement immediately before the air content is determined, since this is a known volume of concrete. So simple, straightforward. The presence, of entrained air affects the unit weight, since, air contributes to volume, but not to the weight, okay? So the unit weight can be used as an approximate indication of air content for the concrete made with the same materials. The unit weight can also be used to determine the volume of the concrete batch, as you can see in this equation here, which is V equals W over the unit weight. Whereas W is the combined weight of the concrete constituents, including water. Then after that, we can determine the yield from this equation, which is the yield will be the volume per the weight of cement in cubic meter per kilogram. All right. Okay, so we talked about the fresh concrete tests, measurements, the air content, the unit weight, and the yield. And before that, we talked about set in time and slump. Let's now talk about more properties that we are concerned about for the fresh concrete. One is the plastic shrinkage, which is, or rather referred to as the early volume changes. This is basically the pre-hardening shrinkage or pre-setting shrinkage, and it results in cracks. It occurs usually in less than 12 hours of age of the concrete. The cracks typically develop due to reduction of volume in the fresh state. These plastic shrinkage cracks are typically run parallel, about 1 to 3 feet apart, and about 1 to 2 inches deep. Okay, but also they can be irregular. I mean, one of the indication of plastic shrinkage usually is the parallel, almost uniformly spaced cracks, but sometimes they are also irregular, right? These also, they may not be detrimental in terms of the structural capacity of the concrete, but they make the concrete vulnerable to other forms of attack. As you can see here, they can be 1 to 2 inches deep. So if they are not really addressed immediately, they might cause a problem later. So the presence of plastic shrinkage cracks must be addressed right away. Okay, before we address them, it is really better to prevent them. Okay, so this prevention is the best cure. Why do they happen? They happen because loss of water at the surface of the concrete occurs faster than the bleed water becomes available. You remember we talked about bleeding? It also can occur due to absorption of water by subgrade or aggregates, and that will cause volume reduction. It is a function of temperature, relative humidity, and wind speed, as we're going to see in a bit. The rapid water loss by evaporation, and we said, this can be exacerbated by, the high temperature, low humidity, or high winds. At this age, the concrete, we said less than 12 hours, is too stiff to flow, but it did not really develop enough strength that exceeds the tensile stress generated by shrinkage. So the concrete will shrink while still in the plastic stage, but it's still not strong enough to resist, the tensile stresses generated by this shrinkage. So one more thing we can also prevent is the absorption, by water by subgrade or aggregate, by wetting them down, especially if the weather is too hot or dry, in order to make sure no excess water is absorbed and taken away from the concrete. Okay? As I said, prevention is the best cure, because although they may not be really that harmful if they addressed right away, but it's better if we can prevent them from happening to begin with. Okay, so the ACI here, or the PCA rather, prepared this tool, this nomograph, which really can help us predict the plastic shrinkage potential in any particular job, so that we can make the necessary measures, or take the necessary measures. This one here, it will tell you that the rate of evaporation must be less than 0.02 pound per square foot per hour. Okay, if the evaporation rate is more than that based on the use of this nomograph, then something has to be done. And how to use this chart, basically what we do, we enter with the air temperature, and then we go to the curve of the relative humidity, and if we come between the curves, we have to interpolate. Then we move right to the curves of the concrete temperature. Again, you might have to interpolate. We hit the value here. Then we go down here to the wind velocity. Then we move left, we read the rate of evaporation, pound per foot square per hour. Okay? Now, if it is more than 0.2, you cannot just say we cannot pour concrete. No, otherwise we will never pour concrete in certain climates. You have to do certain things to reduce this rate of evaporation to a value less than 0.2 in order to be able to meet the requirements. So we have to mitigate these factors in order to make our conditions, conducive to pour the concrete. One thing we can do, for example, moisten the subgrade and the forms, as I said previously. We can erect, wind barriers maybe in order to reduce the impact of the wind on the concrete, because the higher the wind velocity, the higher the evaporation rate will be. We can also cool the concrete by using ice to make sure the concrete temperature, which is again, this is a factor, we can reduce it by using ice. We can spray water, basically, to reduce evaporation from the concrete itself. We can use membrane coating. I mean, yes, concrete in hot weather is really a challenge, but there are many things we can do to mitigate its effect. And also we must know what really what are the factors that we need to control in order to make sure we remain within the allowable parameters and are able to carry on with the concrete in operations. Okay, so basically this is the end of this lecture. This is lecture 28, and by this we have finished the fresh properties of the concrete module, and next time we are going to start on the next module, which is, I think, the mixed design. So I thank you for watching, and I will see you next time. Thanks.